This is just a short little video on something we started at the very beginning of this chapter, talking about the differences between an average rate of change, slope of a secant line on a graph, and an instantaneous rate, the slope of a tangent line, also known as a derivative, um, also on a graph. But I want to also present it how it appears sometimes on the AP exam, and a lot of times it appears in a verbal or tabular format, and I want to make sure you're prepared for that. It's very easy. But just to make sure, it says from algebra, the average rate of change of a line is its slope. That's how it's changing, how the y's change as the x's change. It says the average rate of change of a function over an interval from a to b is simply the slope of the secant line. So we talked about that already. This should not be anything earth-shattering, but the AROC versus IROC is a pretty important concept in here, especially when we get to our word problems, understanding what it means, the average rate that something's changing versus the instantaneous. So just one more time with this. So we have some interval from A to B, should actually be closed if I'm being super picky, and we have some function where the y values represent f of x. So this right here would be at a y value of f of a. This up here would be at a y value of f of b. Consequently, the points are a f of a and b f of b. So we have something changing. In this case, we talk about change in y over change in x. I told you when it goes to the word problems, the x-axis is always a time axis. So time goes by, and something else over here is changing. For our particle motion problems, maybe I'm graphing a distance or a feet. So I'd be doing change in feet over change in time. So that'd be like feet per second, and I'd be looking at the slope representing velocity. But again, along this red line, it would just be its average. It's not the velocity at a given instant, it's averaged over time. And we say that that slope of that secant line, or that average rate of change, is f of b, the change in y's, over the change in x's. But again, this just gives us an average, which is an estimate. Our actual slope right here is very steep. Those two red lines are not close to each other. However, if I could again move that time interval or move that x interval closer, it would approach it. And that's what we're working on with our formal definition of the derivative. From some past AP tests, I cut the year off of this one, so I'm not, and again, your AP FRQs usually have 3 to 4 parts, and they're scored out of 9. Obviously, we can't do a whole one right now. We're not even done with derivatives, but this question would be doable for you right now. So I want to explain the notation and how you approach one like this. It's actually really a simple question. I'm surprised though how many kids leave it blank. The temperature of water in a tub T is modeled by a strictly increasing twice differentiable. These are for questions that came later in parts B, C, and D. It has nothing to do with part A. So this is what I call the stem of the problem. It gives you all the information needed for the entire problem. We're only doing part A. W of T is measured in degrees Fahrenheit, so I'm charting the temperature of the water as minutes go by. We are given a starting temperature both in the stem of the problem and on the table, which means that's really important for one of the questions, not for part A though. We're heating the water for 30 minutes, and we've selected times for the first 20. So these are giving the temperature of water in a tub, and it's going up. And the question says, use the data to estimate W prime of 12. And again, when we see this, this means the derivative. A derivative is a slope of a tangent line. It's a rate of change. So we go up here and we say, well, what's happening at 12? And the answer is, I don't know. They didn't tell me at 12 minutes what's happening. But I need to figure out the derivative. Like, what would the rate of change be? And a rate of change would be change in temperature over change in minutes. So again, you got to figure out what's happening here. We have a T in minutes and a temperature being taken. It's strictly increasing. My question was, well, what rate is it at 12 when it's not on my table? And that's why it says to estimate. So when we do these, I say to do what I call straddle it. So I don't want to be way apart on that secant line. I want to be as close to 12 as possible. So I will use these two to do what I call my average rate of change. And that's why it says estimate. I can't figure out the exact rate of change at 12 minutes, but I can certainly get very close. So you go right next door. And so you're going to say W prime of 12. If we were to write it with Leibniz notation, which I'm going to, would be the rate that the water temperature is changing as time goes by. And we're going to figure out what that is at time t equals 12. Again, I just like you to get used to notational fluency. So I go here and I do, well, see how this Leibniz notation tells me I need to do a change or a difference in W. So you do the old school Y2 minus Y1. I'm figuring out the amount that the temperature changed. This one was calculator active, actually. When you take the AP exam, you'll know number 1 and number 2, you will have a calculator. So although you could do that by hand, I wouldn't. And you'll get a 6.1. And let's put a label on that. That's degrees Fahrenheit. So I'm going to write degree Fahrenheit. And then on the bottom, I'm going to do 15 minus 9, which is 6. Now I can divide those out if I want, or I can just leave it. So it's 6.1 divided by 6. If you're going to round it, remember we go to a minimum of 3 decimal places, either rounded or truncated. This was repeated, so I'm going to go like that. What does this mean? It means that the temperature is increasing at a rate of 1 degree per minute at the time when t, or at 12 minutes. So let's see what this says. Show the computations that lead to your answer. If I was the AP reader for yours, I would have given you 1 point right here. This is not a computation, so make sure you actually show what you're doing. Using correct units, I wrote it here so I'd get credit, but you should actually write it here too. We could do degrees Fahrenheit, and this should have been over minutes, or we can write degrees per minute, and they probably won't mark it wrong if you didn't put Fahrenheit, but then it also says interpret the meaning. So this would have been 3 points, 1 for the computation, 1 for the correct label, and 1 for the meaning. What did I just found? I found a derivative. It was an estimate. I found the slope of the secant line as close as possible. So I just did my change in y over change in x in this scenario, change in temperature over change in time. And I got that 1.06. So I'm going to say you should always reference the time. At t equals 12 minutes, the temperature is increasing at about a rate of, or approximately a rate of, or even at an average rate of 1.106 degrees Fahrenheit, technically, per minute. So not a hard question mathematically. I had to subtract some numbers, but again, the theory behind it is I didn't know what was happening at 12, and I take the neighbors. And again, graphically, it's because if we want to know what's happening exactly at 12, I could grab 2 points for an average rate of change, but make sure they're as close as possible so that your estimate is the best it can be. So that one's done. Let's go to the next one, and it's very similar. So now this, I did put the year on. It's 2011, the year before I started teaching this. This would have been part A of their second question, and you notice it's so similar. So now we have a pot of tea cooling instead of a tub of water heating. So again, what does it say we're supposed to do? Use the data on the table to approximate the rate at which the temperature of the tea is changing at 3.5. So approximate the rate. What would the rate be? Well, a rate is a slope. we have the instantaneous rate of change, which is the derivative, and the average rate of change, which is the slope of the secant line. Well, we're supposed to approximate the rate that it's changing at a time that's, again, not at the on the table, but it's right between these two. So we're going to deal just with this small window and get the slope of the secant line, show the computations. I'm going to do 52 minus 60 over 5 minus 2. What that means is the temperature went down 8 degrees over the course of 3 minutes. I can leave that like that, or I can write it as a decimal. Maybe you want to write it as negative 2 2/3 or negative 2.6 repeated. It doesn't matter. This also would have been calculator active, so each is fine. I showed the computation. It does not say to show a correct label, which means there wouldn't be a point for it, but you should know what it is. This would be negative 6.2 degrees Celsius per minute. So degrees Celsius per minute. Or if you're going to write it when it's in ratio format, put degrees Celsius over minutes. Then it says, show the, oh, that's it. It just says show the computation. This was probably only worth 1 point, to be honest. But if I were asked to describe what this means, I'd say the temperature is cooling at a rate of 2.6 degrees Celsius per minute. Notice I didn't say cooling at a rate of negative. You got to be very careful. I can say changing at a rate of negative 2.6. I could say but I can't say decreasing at a rate of negative 2. This sucks up the word decreasing or cooling or any of that. So be very careful when you're asked to write it. But this didn't say that. But I kind of want to repeat what I just said, and then that'll be the end of it. If it did say this, you would say the temperature is, now if you say changing, then you can use the sign in your analysis. So I'm going to put is changing at a rate, and this is at about a rate of, or you could put at an average rate, that wouldn't matter, at a rate of about negative 2.6 degrees Celsius per minute. All right. Now, had I changed this word, and this is, you might say, they're so picky. It actually is not correct if you say is decreasing at a rate of, you can't put the negative in there. The decreasing covers that. Otherwise, it's a double negative. Or if you said is cooling at a rate of negative, you can't do that. So I suggest the word changing so that you can put the sign of your answer in your explanation. But again, as I said, for this year, it just says show the computations that lead to your answer. This would have been one and done. All right. The last one would have been 3 because it said to show the computations, give an appropriate label, and explain what it meant in the context of the problem. So this is done. I'll make sure you've taken these notes tomorrow. If you want to, if you get them done today, you can just come and show me now. We've got worksheet 2.C out there. We've got a little Delta Math out there, but have a good one.